So this is the second one in a series of 3 discussions of spatial panels. I could have a whole course devoted to spatial panels. And as I mentioned in the first lecture, we're just, because we're constrained in time, we're going to limit ourselves to so-called static panels. So these are panels that focus on the cross-sectional dimension and don't bring in time-lagged explanatory variables of one kind or another. So what we did last time was basically go over the data structure of spatial panels, which is in essence the traditional econometric panel structure flipped around. So the organization is one cross-section at a time for each time period rather than little time series for each cross-section. So those are the, that's the typical paradigm in space. It's all flipped around. Then we looked at a number of different types of model specifications, fixed effects versus random effects, which we'll revisit today, and a little bit about dynamic panels or space-time panels, and then the simplest way of modeling spatial effects in panels, which is simply pooling the data and in essence forcing the same model on each cross-section so that you, even though it looks like space-time data set, it's really a series of cross-sectional analysis that all use the same weights matrix and all have the same parameters. So the tricky part there, if you have had panel data econometrics before, is that all the Kronecker products seem backwards, they seem flipped, and so it takes a little while to get used to that notation. So today we'll do more of that. We'll focus on the fixed and random effects specifications, and then on Wednesday we'll look at spatial seemingly unrelated regressions, which is kind of in between these specifications. So we go over fixed effects models, how they're set up, how you incorporate spatial lag error in those, random effects models, basically the model specification, and then we'll go into a little bit of detail into 3 major estimation paradigms: the maximum likelihood, which we've already seen before. It's always the same thing. You specify the likelihood function and you maximize it. Then a more robust, less parametric, if you wish, instrumental variables, 2-stage least squares approach, the error components, 2-stage least squares. There's actually a whole bunch of estimators for that case, but I'll just give you a taste of one. They're all very similar. And then the generalized methods of moments estimation, which is a generalization of what we've already seen in the cross-sectional case. In the cross-sectional case, we saw that applied to the error specification. This is the same thing, but for multiple equations, if you wish. And then very briefly, because this stuff is extremely complicated and the notation is a bear, as you'll see, I'll just give you one example, talk about specification tests. And I don't have enough time to go into that in much detail. And also, there's a bit of a problem with this. So the main piece of software to estimate these models would be the R SPLM package. But there's some issues with that, with larger data sets, such as the US counties. You know, I could not get it to converge for a number of these models, so, you know, we're not going to go there. When we have a little more stable software, we might revisit it. And then in terms of the readings, pretty much the same as last time, this review chapter in 2008, and then there's some technical papers. If you really want to dig in, there's the paper by Kapoor, Collegian, and Prucha, which is kind of a very clever way of working around the problems of estimating these models. So basically the original specification, which in the days I suggested, is very difficult to estimate because of the interaction between the parameters. So they kind of worked around that and suggested an alternative. It's an alternative, Which of the two is more relevant is an empirical matter. There's no theoretical basis to choose one over the other, but they are different models of spatial effects. And then the two Baltagi et al. Papers give you all the technical detail you ever wanted and then some about these Lagrange multiplier tests. And then the last piece, I just put in the Journal of Statistical Software piece on the SPLM package so you get an idea of what it does and how it approaches things. So let's start with the fixed effects models. And fixed effects are a bit of a problem with spatial dependence added in because, as I mentioned the other day, we have an issue of potentially incidental parameters. So for the spatial models, we get the asymptotics by going to the limit in the cross-section, by going to the limit with n. And fixed effects are individual specific or location specific. So we have unobserved heterogeneity, which is specific to each location. Let's say there is a county effect that you cannot somehow quantify, but it's there. So then you stick it in as an additional dummy variable. Each county gets its own dummy variable. And so this is not going to work too well if your time series are super short, but it is a way to put in the individual effects. For large n, or for asymptotics with n, you have an incidental parameter problem because there is a new dummy for each additional observation. So as you go to the limit, you get more and more dummies that you need to estimate. And so typically, these additional intercepts or these dummy variable coefficients cannot be estimated consistently. Even though you can come up with an estimate, and it's often done, these estimates are not very reliable. And you can sort of see why that is. If you have more and more of these individual effects and the time series are very short, you don't have a lot of information to extract the parameter. So the focus in the fixed effects models, and actually also in the random effects models, but for a different reason, the focus is on the betas. So on the slope coefficients, not so much on the individual intercepts. So the idea is that in the model, we capture the individual heterogeneity by adding an additional intercept. And so here we have to be careful, and there are really two ways of dealing with this. One is to keep your overall constant, and then force your intercepts to sum to 0 or something arbitrary like that, so that you really take in 1 degree of freedom out of it. The other alternative, which is a little easier to do, is to keep your overall intercept and then have one less individual dummy. So you take one location, one region, one individual as the benchmark, and then you have dummies for all the other ones. Another approach is to not have an overall constant term and just have n individual dummies, one for each location. So you have to think about this. In practice, these dummies are seldom actually reported even, because when you have a very large number of observations, even though you could have unobserved individual heterogeneity, who's going to report 10,000 individual dummy coefficients, right? And what kind of sense are you going to make out of that? So this is different from the spatial fixed effects that I mentioned in another context, which are more of a multi-level fixed effect. So all the counties in the same state get a state dummy. That's a spatial fixed effect. So that doesn't suffer from the incidental parameter problem, because presumably the number of states is much smaller than n. So if n goes to the limit, the number of states may also grow, but it doesn't grow nearly as fast. So we're in good shape there. Here, we clearly have an incidental parameter problem if we go to the limit in n. So the notation again, to get us back to the matrix notation, the dependent variable is an n by t vector. The X matrix is an n by t by k matrix. The remaining error term is an n by t vector. And then this here, you have to think about this as a cross-section of individual fixed effects for one time, one period at a time. So this is the Kronecker. IT is a vector of ones of the length of the number of time periods. So each, because of the Kronecker setup, each of these ones is multiplied with a n by 1 vector of the individual effects. So we're stacking these individual effects on top of each other. They're constant. They're the same over time. So then how do we get spatial effects in these models? And we'll look at the two cases, the lag model and the error model. And this looks an awful lot like what we saw last week in the pooled case, except for this part, right? So the first part is the spatially lag dependent variable that we introduce for each time period. So you can think of this as a lag regression for each time period, but the autoregressive coefficient, the rho, doesn't have a t subscript, so that's the same rho in all times. Same for the betas, no t subscript. And then our alpha vector is again our individual fixed effects. So then if we go for the full notation, we get the Kronecker of an identity vector with the time periods, so 1, 1, 1, 1 on the diagonal. Each of these diagonals gets multiplied by the same weights matrix. We talked about this last time as well. Same weights matrix. Constant autoregressive coefficient. Then this x beta plus error term is the same thing. And this is the same expression as we had before. So that's our short vector of ones, Kronekert, with the long vector of the individual fixed effects. Okay. Then the error fixed effects is even simpler, if you wish, because we have the same thing. We have the regression for each time period, but then the error term in each time period shows a spatial autoregressive process. And this is exactly the same thing as what we had previously in the pooled model. So this inverse is, if you wish, the reduced form. And we have used and will call this expression the spatial filter, if you wish, with the spatial autoregressive parameter lambda. We'll call that B in our notation, because this comes back with transposes and all that stuff. So this is all nothing really special to it, except for this additional set of n fixed effect intercepts, if you wish. And they're just intercepts. So that's also something to keep in mind. So the way that the fixed effects model conceptualize the individual heterogeneity is in terms of the shift in level. No shift in slope. So the betas are the same everywhere, but the alphas are different by individual. So whatever is this unobserved heterogeneity, it gets absorbed by this shift in intercept. One advantage of the fixed effects specification, which I also mentioned last time, is that the fixed effects, these are unobserved, so we can't actually measure them. We just kind of catch them in this intercept. They can be correlated with the other explanatory variables. The random effects, as we'll see in a few minutes, cannot, because the random effects go in the error term, and the error term should not be correlated with the other explanatory variables. Otherwise, you have an endogeneity problem. So the way the fixed effects are approached, and this is very general principle, is through a so-called within estimator. And think of the following. So if you have data for, let's say, 4 time periods, right, and you have a fixed effect constant, that's the same value for an individual for each time period. And you take the average of that fixed effects over the time periods, that's going to be the same constant. Then you take the deviations from the time mean, that's going to be 0. So this is called, depending on the literature, demeaning or within estimation. And so basically, this wipes out anything that is constant over time. So what's left is what actually varies over time, but measured as deviations from its time mean. That doesn't really matter, it's just a scaling thing. It doesn't affect beta at all. Beta is the same. You know, you may have, I mean, in fact, for some of you, I suggested this, when your variables are in very different scales, then your coefficients look weird. Some are, say, 2.5, and then another one would be 0.000000008. You know, just rescale your x variables, and they all look more or less the same. This is a similar principle. You're just rescaling the x variables. The betas are not affected. So typically, the demeaning operator in the panel data literature is expressed as a vector q, which is an NT, a matrix, I should say, q, which is an NT by NT matrix, big one. And whenever I say that, you should think, oh, how does this scale to large data? Well, there's lots of tricks to actually avoid having to deal with NT by NT, and typically to try to limit something to an n dimension or a t dimension if you can. So the thing about this demeaning operator, and we'll see it in matrix notation in a second, is that when applied to constant vector, it just wipes everything out and you have 0, right? So as a result, this within estimator, which is basically a different regression. So you can think of, you have your original setup, you express everything in deviations from the time mean, then you have a regression without a constant term, because the constants are all gone, but the beta is the same beta as in the original specification. So you get a consistent estimate for the beta. Of course, the alphas are not relevant. Okay. So this, I said, I promised this, matrix notation for the demeaning operator. And the reason that I bring this up and keep hammering on this is because if you're familiar with panel data, you're familiar with this expression, not that expression. And if you look carefully, it's just flipped around. The order is flipped around. And the order is flipped around because we flipped around the organization of the data. So if you have little time series, one for each cross-section, then it's very easy to get the mean over time. If you have them organized as cross-sections for different time periods, then you have to keep track of the same cross-section at different points in time. So that makes this kind of weird looking because this IT by IT prime, so that's a vector of ones times a column vector of ones times a row vector of ones, so that's a square, t by t square of ones, right? And each of these t by t one elements of 1 get multiplied by a diagonal matrix of dimension n. So if you have, say, 2 time periods, there's a diagonal, a diagonal, a diagonal, a diagonal. So that's very, you know, a little bit awkward, different, but still correct, because that diagonal ensures that the mean is taken, which is the over t, and that because it's subtracted from 1, it's, you know, if you multiply this with the variable, it's the variable less its time average. So that's exactly what we want. So this wipes out the effect of the constant. This is called the within estimator or the demeaning operator. And the way you get it is with the demeaning operator. There's also a between estimator. And I don't have it as a slide, I'll get back to it later. A between estimator is going even further and is taking the mean of everything, the time mean. And so that is an alternative way of dealing with this as well. So the properties of this matrix, I can't help myself. It's an idempotent matrix. Idempotent matrices are fun because you can multiply them by each other and transpose and do whatever, and it's always the same thing. The bad news is that they're singular. So you can't get an inverse. The determinant is 0. And this will come back to bite us in a few seconds. You can carry out a generalized inverse. It's important to get the intuition straight that a generalized inverse is not an inverse. The way I like to put it, I mean, a lot of people get confused by this. They say, oh, no problem, we can't do an inverse, we'll do a generalized inverse. Well, an inverse is an exact solution. A generalized inverse is like a least squares fit. It's not the same thing. So, I mean, it's a generalization of this concept. If you look at the geometry, it's the same kind of idea, but it's not the same thing. An inverse is exact. You know, it's like saying, what's the inverse of 2? The inverse of 2 is a half. You know, what's the inverse of some weird number? You know, you can get as close to it as possible, but it's not going to be exact. So that's just a little aside. So now we get to the real meat. How do we estimate these models? So we take the demeaning operator, Q, and we apply it to everything. And lucky for us, the Q times the spatial lag is the spatial lag of Qy. So these are interchangeable. And so the same thing holds for X, the same thing holds for the error terms. So lucky for us, we can pre-multiply this spatial lag expression with this Q matrix, and it basically has the same form, except that we do everything with Qy, WQy, Qx, and Q error term. But there's a catch. And this catch comes back when we try to do maximum likelihood. Unlike what you might have seen in the literature, this is not a valid distribution for an error term. Because the new error term, the demeaned error term, does not have a non-singular variance matrix. In fact, the variance matrix doesn't exist. Right? So that is not a standard result, and you have to deal with that if you want to do maximum likelihood, and that's why I don't even want to talk about maximum likelihood in this model. There's a literature out there, but I'd say, you know, not worth the effort. Error model, same idea. You know, again, lucky for us, these transformations do not affect the model specification as such, but we have the same problem. At the end of the day, the error variance covariance matrix is singular. Inverse doesn't exist. So you can get a generalized inverse, but it's not quite the same thing. Right? So what's the moral of the story for the fixed effects? They're actually very intuitive specification to deal with unobserved individual heterogeneity. In the spatial models, the way to deal with them is demeaning the variables, but then use a method that doesn't require a full specification of the error term, because the demeaned error term doesn't have a proper variance. So then you have to deal with this. And there are ways to deal with this, very technical ways with different transformations that let you do maximum likelihood, but you lose a degree of freedom whether you like it or not. I mean, that has to be dealt with. So most of the attention in the literature has been focused on random effects, and it's, you know, basically the same thing whether you call this alpha I or mu I. I mean, in terms of the notation, it's the same thing. Conceptually, it's fundamentally different. So rather than including a dummy variable, an indicator variable as one of the variables, as one of the explanatory variables, one of the x's, now we put the heterogeneity in the error term. So now we have two error terms, one that is specific to each individual, this mu of I, and then one that is kind of generic. It's referred to as idiosyncratic. So basically, the leftover, right? The individual one is individual specific and doesn't change over time. That's the same as the dummy variable fixed effects. It doesn't change over time. Important to keep in mind. The other one does change over time. So one only has an I subscript, The other one has both subscripts, I and T. So for each cross-section, we have this new composite error term, and then we can write it just as we've been writing everything. It's the exact same thing, but instead of alpha, we have mu here. Right? So then what does that do to us? It creates a complicated variance-covariance matrix. And in fact, we have the two components, the individual specific component that doesn't change over time, and then the component that does change over time. We use the standard notation. We work this out. The typical assumption is that the individual unobserved heterogeneity and the error term are not correlated, and so that there's no covariance between them. Then the overall variance takes on this form, which is again a little flipped around relative to the standard textbook result. But we have this variance of the time varying error term times a very long matrix, identity matrix. And then we have this variance of the individual heterogeneity. So that is kind of the within variability that is constant over time. And we just rescale that using this Kronecker product. So that this creates a kind of a serial correlation over time of a block nature. So that's a little bit different. So that's basically the problem here in terms of estimation, and these are standard results. But again, the Kroneckers are a little bit different from the textbook because of the spatial arrangement of the data, is that, if you use fancy results from linear algebra, you can actually figure out that the determinant has a simplified form, as does the inverse. So we do not have to invert an NT by NT variance covariance matrix, right? So the sigma, the full variance covariance matrix, is of dimension of the space-time dimension, NT by NT. That's a monster. You don't want to invert that. And we don't have to, because here there's actually no matrix inverse involved in this. We get the matrices through the Kronecker products. These are all scalars. That's the variance of the within variance, and that's the between variance. So these are all scalars. We get the matrices from these blocks of ones and identity matrices. That's one of the most powerful results in the estimation of panel data of random effects kind. And so then you can actually run one of these models, and I have a bunch of illustrations. I didn't give you a notebook because I don't feel, I don't want to get deluged with a bunch of complaints. This doesn't converge, this blows up. One of these, I mentioned it the other day, one of these I ran for 10 hours and it still wouldn't converge. So it's no way am I doing this. So, but it does work sometimes. So this is a very simple specification that we've used before, and this is the standard maximum likelihood panel estimation with random effects. And so these are the coefficients. I stuck in some time dummies, which you can easily do. And then here are the kind of results that you have to extract from in R from the object. So this is a typical simplification that to reduce the number of parameters, the ratio of the within variance over the between variance is used as a parameter. And then using these expressions that we just have here, these kinds of expressions, you can extract all the parts. And so we have within variance and between variance. And so then the total variance is the sum of these. And because it's maximum likelihood, just for reference purposes, I put the likelihood here so we can compare it in a few minutes with some of the spatial models. So then that's a standard model, a random effects model. We can have a spatial lag model with that. It's basically the same thing. The only thing added is this endogenous spatially lag dependent variable. The variance has exactly the same expression. So there's really, nothing to that. If you can estimate a random effects model with endogenous variables, you can estimate a spatial lag random effects model. And in fact, one of the estimation methods that we'll see takes advantage of that in terms of a two-stage least squares estimator. So spatial error autocorrelation, on the other hand, is not so easy. Right? And here we have basically 3 ways of introducing spatial autocorrelation in a random effects specification. And as I mentioned before, so the full error term has 2 components. A within variance random component, this is fixed over time, and then another one that varies over time. And so we can do the traditional way of doing this in the panel literature originally in terms of time series correlation was to put the time series dependence in the remaining error term. So in my way back one book, I did the same thing and put a spatial autoregressive process in that error term. Then the Kapoor paper that came out about 15 years ago did a little bit different and had the autoregressive process apply to the full error term. So rather than applying it to this, it applied to both of these together. So there was a spatial autocorrelation both in the time varying effects, but also in the individual heterogeneity. There was autocorrelation in the unobserved individual effects, which, the first one doesn't have that, right? The first one has the individual effects are whatever they are, they're not correlated. And then the correlation, whatever correlation there might be, is relegated to the remaining term. And then Baltagi, if you're going to do anything with panel data, you have to look at this Baltagi panel data econometrics textbook. He has had an idea of an encompassing specification, which is kind of a compromise between the two. So let's look at what each of these does. So the first one, we start with the error term, the within random effect, the remaining time varying random effect, and then we have the usual spatial autoregressive process in the time varying random effect, right? And here's our B as a simplifying notation. Then we can express this time varying error term in each time period, and that's very important, in each time period as B inverse time the remaining error term. So then for all the time periods, we have our friend the identity matrix Croneckered with this B inverse. So that's a block matrix, B inverse, B inverse, B inverse, and so on, right? The rest is standard, the standard random effects part. And so then, you put these pieces together. These are 2 random components. This randomness in U and the randomness in the random effects are not correlated. So it's easy to get the variance. There's 2 variance components, if you wish. And so some of the early literature on this was called variance components. So you have this one with the individual heterogeneity fixed over time, and then this is the variance of the remainder, which has this kind of interesting additional parameter. The autoregressive parameter is in here, in the B, or in the B prime B, if you wish. So then the second approach, the Kapoor, Collegian, and Prucha approach, is to apply the spatial autoregressive process to the whole error term. Right. So then we have the usual autoregressive process in the same we saw in the pooled model. It's with this Kronecker, same parameter in each time period, same weight matrix in each time period. and then a remaining error term. So then the expression is a little bit different because now it applies to this full error term, which in turn contains the random effect plus whatever else is left. So it's a little bit different way of thinking. In the first model, we keep the random effect uncorrelated, and then whatever spatial effects is in whatever is left. Here we say the whole thing, the random effect plus whatever is left, is spatially correlated. And so then the transformation applies to this composite error term, and it becomes a little more complicated, but in fact, this is the standard random effects specification for the error term. The B-1 transformation is applied to this whole thing, one period at a time. And then the variance, as it turns out, this may look complicated, but it's actually much simpler than the other one. So these are two transformations. This is the Q naught is the one that we know. It's the deviations. This may be a typo. I can't remember whether this is divided by t or not. And then Q1 is the average over time. And then each of these have a variance term associated with this. And this you may recognize from the standard panel expression. It's the random effects variance and the random effects variance and the remaining variance, sorry. So this is multiplied by t for every time period. The other one is for all the time periods. So this looks complicated, but in fact it's a lot easier to estimate, and this specification tends to converge. The other one does not. And then, so what difference is this? As I mentioned, in the classic specification, I should say, the spatial spillovers are only in the time varying errors, and in the second specification, they're both in the random effect, the individual heterogeneity, as well as what is left. And so there's really two different ways of thinking about spatial effects. Which one is better? That's an empirical matter, right? And I should point out, this is about the error term. This is not about the model itself. So, as I've said many times, as our data sets are getting larger, this is becoming less and less relevant, because in very large data sets, the effect of the error structure is on precision. And if you have huge data sets, you have precision. You don't have to worry about this. So this is kind of comes from an older literature. It's still relevant, but not as relevant as it used to be. And so Baltagi came up with this model, which is kind of cool. He just said, well, let's have two separate spatial autoregressive processes, one explicitly for the random effect, for the mu, and one explicitly for the other part, the time varying part. So this is not time varying, that's why it calls it permanent, and this one is time varying. And then you have a composite error that basically has the two terms, with a B inverse here and an A inverse there. So then you can test and you can say, well, you know, is theta 1 0? Is theta 2 0? Are both of them 0? You know, then you can test these constraints on the variance. But you see this variance expression, again, is going to be a bit of a bear because the parameters are inside these inverse terms. Okay, how do we estimate these models? So we have the fixed effect ones, which I'm not going to talk about anymore. You demean, and then, you know, it's up to you. The random effects ones, we have three ways of going about it, basically. So the maximum likelihood estimation, if you looked at this very carefully, this is nothing but a special case of a non-spherical error variance matrix. So this is all going to be special cases of feasible generalized least squares. You know, we've already seen this as spatially weighted least squares earlier on. Problem is that the log likelihood function is going to be pretty complicated, and we'll see a couple of examples of that soon. Second strategy is throw away the assumptions behind maximum likelihood, the full parameterization, normal distribution, and all that stuff, and just go deal with the endogeneity. That only really works for the lag model. We know the lag model is a special case of endogeneity, so if we have the right instruments, we can do this, and in fact, we can show that we can estimate the lag model as a special case of Baltagi's error components two-stage least squares. There's at least 2 or 3 other alternative ways. Basically, these are all approaches to get at the components of the feasible generalized least squares estimator. And so if you remember in this spatial error model, the cross-sectional one, a feasible generalized least squares, we needed a consistent estimate of the spatial parameter, and then we plugged that in there, and in the spatial cases it was simple filtering of the variables, and we're good to go. Here it's a little more difficult. We need a consistent estimate of the sigma square mu and sigma square u, so the 2 components of the variance. So once we get these, we can plot them in a feasible generalized least squares or its extension to two-stage least squares, which is pretty much the same idea, but a little bit more complicated. So how do we go about it? We'll see that in a few minutes. And then the third one, so the first one, maximum likelihood, applies to lag and error specifications. The second one, the two-stage least squares, applies to the lag model. And the third one, the generalized moments, applies to the error model. And now we're going to have fun. So the spatial lag model, basically it's a standard linear regression model, but we need to add 2 pieces. We need to add the Jacobian. Remember the Jacobian in maximum likelihood estimation? It was the I minus rho W determinant. Now we have to put that in there t times. I mean, you can think of the Jacobian of a determinant of a block diagonal matrix. So if you're good with your linear algebra, since it's the same block each time, that simplifies greatly, and you can just, it's to the power t, but if you take the logs, it's t times the log of that determinant. So this is our Jacobian term, counterpart in panel data, and then we still need to deal with the error variance covariance matrix, both here as a determinant and here as an inverse. And we saw a few slides ago that, lucky for us, both this determinant and the inverse have simplified expressions that don't involve any matrices. So we plug that in here for the determinant, plug it in here for the inverse. And that is the standard case. So the spatial lag part is encompassed in the Jacobian term, and the error components part is encompassed in these specialized variance matrices. And then we can just throw that into a likelihood process. And so this is an example of the estimation. The terminology is a little bit off for one reason. I don't know why they started calling rho lambda and lambda rho, but whatever. I'm sticking to my notation. So rho is the autoregressive coefficient in the spatial lag model. It's maximum likelihood, so you have, they call it lambda, but that's really rho. So they have everything, standard error, asymptotic standard error. The phi is again this ratio of the random effects variance over the, so within variance and between variance as it's called. And then these are the individual components. And you see these don't vary too much from what we had before in the model without the lag, right? And at the end I'll show you all the results next to each other. But so this, also this is quite a bit better than previously. So the lag actually adds to the explanatory power. So the whole point of this estimation is to get a consistent estimate of all the parameters, taking into account this additional structure that we have here due to the random components, right? And the standard pooled model ignores all this. The standard pooled model does not deal with individual heterogeneity, right? Now, one way you could deal with this in the standard pooled model is just say, the hell with this, I don't really care what these components are, I'm going to use a white type standard error estimate. And we saw that the other day. You can, in fact, do this. So then, spatial error with error components, as I mentioned, there's a number of different flavors. I'll just show you real quickly how complicated this gets. This is the generic expression. This is a log likelihood for any regression model with a non-spherical error variance covariance matrix. So 2 pieces to it, the log of the determinant of the variance matrix and the inverse of the variance. This is of the dimensions of the data. So this NT by NT, this is NT by NT, right? And now the problem is that these variances, we can express them in a simpler form, but we do not get the result that we have in the standard case where there's just scalars. We still end up with having this to deal with. So this B prime B is of dimension n by n, not nt by nt, but still not a scalar either. So you work out the variance term, you have these 2 components with all these inverses. You can simplify it a bit, but still, you know, you have the ratio here of the 2 variances, and the spatial parameter is in here. So basically, this is a monster. You need a determinant. You can show after a lot of algebra that the determinant does only involve matrices of dimension n by n, which is better than nt by nt, but it's still pretty bad, right? And that's why this doesn't converge readily. And then the inverse, same thing, you know. So you can have fun and look at these equations, but at the end of the day, it may be overkill, you know, especially with larger data sets. And then the likelihood, and I'm trying to be nice here, often fails to converge, you know. I actually managed to get it to converge on a simpler model last year when I taught this. So I actually have an example where it does converge, but it's a different model. It's much, none of these models with the Nat regimes data, and I spent a lot of time trying this, I could not get them to converge. It just keeps running. So this is an understatement. It's a complex optimization problem. So I don't know if this has to do with the way, I mean, the SPLM is very elegant. It's an object-oriented take on things, but in my experience, that's not always the most efficient. I mean, it's very elegant in terms of design, and that you have a generic case and then you have all the special cases coming out of this generic case. In my experience, you often get better performance customizing. I mean, it's not as elegant, but you get the speed if you write the code specific to each case, rather than have one generic case and get them all plugged in. And I suspect that may be part of the problem here. So then the KPP specification, as I mentioned, you know, initially it may look more complicated. In fact, it's a lot easier in terms of the estimation. And this one does converge readily in a few minutes, you know, I think like 5-6 minutes, it converges. And it gives you, of course, what they call rho is what we call lambda. That's the autoregressive parameter. And then we again have the error components. And again, these are in the same order of magnitude. So the components tend to be pretty consistent whether you ignore spatial effects, whether you put in a lag term, or whether you put in an error term. So the second paradigm, if you wish, is the IV two-stage least squares, and it's the same as always. You know, we treat, and this is easily generalizable to the inclusion of other endogenous variables. We just have to have the right instruments. So the spatial part is that we need instruments for the spatially lag dependent variable, and these are the spatially lagged x variables. We have some, you have to think about, do you use them all? Do you use them, how do you combine the different time periods and all that kind of stuff? But basically, that's easy to do. We've done this before. Then the actual estimator, I didn't write it out because it's kind of complicated, but it is, you can think of it, you get an estimate from the within estimator, deviations from the mean, and the between estimator, which has the absolute, averages. And then you take the residuals from each of these and then use those to get estimates of these variance components. And then you plug the variance, they're consistent. Then you plug these variance components into a generalized, two-stage least squares, kind of a hybrid between two-stage least squares and generalized least squares. And there's different ways in which you do this, depending on whether you take a 2SLS approach or a GLS approach, and that's what these variants in the literature boil down to. So basically, you start with the within estimator, you do the demeaning and you get it. You get the between estimator, they have these P and Q are orthogonal to each other. Then from each of these residuals, you get these variance components, and you hope that you don't get any negative variance estimates, and then you're good to go. I mean, the negative variances are because, let me see if I can find this really quickly. Yeah, so you see this here, right? So you estimate this one, and then you estimate this one. And then how do you estimate this one? By subtracting this from this and dividing by t. But this subtraction could be negative. And when it is negative, then typically there's obviously something wrong with your specification, and then you shouldn't estimate this model. You should do something else. But this can happen, and again, with larger data sets, it tends not to happen that much. So basically, that's how you do this. You do this three-step process. There are other variants of it. In fact, SPLM includes two other ones, but this is what you would get. And one thing that you can notice, but maybe you didn't think of it, is this is quite a bit different from the maximum likelihood estimate. But then the other pieces are the same pieces. So it's always the same thing. This is the heterogeneity, the cross-sectional heterogeneity, if you wish, and this is the overall heterogeneity, and then this is a measure of spatial correlation for the lag model. And then in the error model, we have the generalized moments estimation, and that is basically the same idea as what we had before, but extended to this particular model. So the idea, just to recap, what is the approach? We know that to get consistent estimation of the betas, you only need a consistent estimate of the nuisance parameters. So you don't need to have necessarily a very precise estimate of the nuisance parameter as long as it's consistent. And in our case, the nuisance parameters, there's three of them. There's these two variance components and a spatial autoregressive coefficient for the error process, right? So the way Kapoor approaches, first of all, they cheat a little bit and get a different specification of the error components, which is actually easier to put in the moment equations. And then they do the same thing as what we've done before, and you have your moment equations. Remember, these are things that hold in the population. So if you look at these expressions in the population, this is your remainder variance. This is the remainder variance with our friends the traces. This is the sum of these two components here with our friends the traces. So we have all these equations, and we can solve these equations because the spatial parameter is in here in these error terms that turn out to be expressions in the residuals, the spatial lags of the residuals, and the second order spatial lag of the residuals. So we get all these residuals, we plug them in there, we solve for the 3 parameters, we plug them into a feasible generalized least squares procedure, and we're done. And so the result looks something like this. As we had in the standard cross-sectional case, there is no standard error for this. So this is a point estimate and a point estimate only. There's no precision associated with it because in the nuisance parameter approach, we don't need to worry about that. As long as we can show that it's consistent, we're good to go in our 2-step procedure. This one is also really easy to estimate, you know, so if you're going to do something, so here they all are together. So the pooled one is the one that we did the other day. We can do this in GeoDa and GeoDa space, no spatial parameters and no variance components, just one variance, right? Say roughly 30. And so then the standard random effects, no spatial effects whatsoever. Again, if you add these up together, it's roughly 30. So you can see very nicely how the overall variance, error variance, decomposes itself in 2 pieces. One piece that is due to unobserved individual heterogeneity, and another piece that's due to the rest, right? And so then basically what we're doing as we're putting in the spatial effects is adjusting this decomposition a little bit, right? Now look at the likelihoods here. So this is the standard one. This is error components much better, lag much, much better, and then spatial error in between somehow, not really that big a deal, right? And so we ML lag and the error components 2-stage least squares, as I pointed out, difference between the coefficients. And what you tend to see is, you know, I mentioned this before, the lag coefficient in essence, you know, eats up part of the values of the other coefficients. So if your lag coefficient is going to be larger, the other coefficients will tend to be smaller. So this is something you basically observe here as well. And then the 2 error estimations are using the KPP specification because the other one doesn't converge. So we have using maximum likelihood and using generalized moments. And you see these are not very different, you know, so this actually works pretty well even though it doesn't assume normality and all these things. So we can do all this stuff. If you're going to do this for your own work, I would suggest, well, in SPLM, I would suggest that you stick with the 2SLS, the more robust and GM form, and definitely if you're going to do anything, use the KPP error specification. The other ones, you know, I need to look at it a little closer. It's been a while, but I think you really need to think about how you estimate that. You know. I had some software at Gauss that did this, but it's a long time ago, and I haven't checked it lately, so I'll have to take another look at that. So then the specification tests, just to close, the this gets really, really unwieldy in terms of notation. You know, it's basically a mess, and that's why I don't want to spend too much time on it. So the tests are all Lagrange multiplier tests, and so it's always the same principle. You get the score, you get the information matrix. So the test is the score transposed, the inverse of the information matrix, and the score again, evaluated at the null. And that's the easy part, right? That's also the hard part here. What is the null? So we have 3 things that could be 0, right? We have the, well, 2. We have the spatial parameter, and then we have the individual heterogeneity component. I mean, in principle, the overall error could be 0 too, but that, you know, doesn't make any sense. So, you know, these 2 could be 0. And so depending on which of these we make 0, we have a different null hypothesis. And in each of these cases, we have to derive the likelihood estimation with all the parameters, and then we impose the constraint, which means we set pieces of it to 0 and then work this thing out. So we can have a null where the null is really everything. So no random effects, no spatial lag, no spatial error, no nothing, right? Or we can have the null being one of these models without the other part. So let's say a standard random effects specification, and you want to check whether there's any remaining autocorrelation, right? Or you have one of the spatial models, and you want to check whether there are any random effects, unobserved heterogeneity that should be taken into account. So all you can see this very quickly, this yields a whole bunch of different combinations, and each of these has their own tests. The terminology of this is to distinguish between what we call marginal, joint, and conditional tests. The marginal test is just a test for one. Remember, all these are tests on a parameter in the model set to 0. So one parameter is set to 0 irrespective of what the other parameters are. That's called a marginal test. A joint test is where all kinds of things are set to 0. So a joint test would be a case where there is no spatial effects and there are no individual heterogeneity. So no sigma square mu, no rho, no lambda. That would be the joint null hypothesis. And then a conditional test is whenever you have one of the models and check for remaining misspecification. So you have a standard random effects model, you check for spatial effects. Or you have a spatial error model, you check for random effects. These are all these combinations. So each of these, as I said, it's a pain in the neck, but you know, the hypotheses, testing for spatial effects no matter what, special for both, testing for both, testing for one in the presence of the other. Right? An understatement, complex expressions. Right? And just to give you a taste, this is the conditional test for a spatial autocorrelated error term, a spatial autoregressive process in the error terms in a model with random components. So we have a standard random components model. We take the residuals of that random components model and put them in this thing. And this thing has a bunch of expressions in this, the ratio of the two variances, you know, the within variance and the between variance. This is our phi in the model, right? And then we have t in there. We have our traces, the trace WW and W prime W. So all this stuff goes in here, and that is chi-square with 1 degree of freedom. And as I said, I am sparing you the pleasure of seeing the other expressions. If you want to see them, go to the Baltagi papers. They're all in there. They're implemented in SPLM, but I've had bad luck getting them to work very well. So again, that may have, I didn't check it again this time around, but when I did this last year, some of these didn't work. So that's where I wanted to keep it for today. So the third step in this is going to be spatial, seemingly unrelated regressions on Wednesday.